Good morning, good afternoon, good evening, everyone. Thank you very much for watching this video lecture. Today, we're gonna study joint probability distribution for discrete random variables. A joint probability distribution describes the probability of two or more random variables taking specific values at the same time. The joint probability distribution is a fundamental concept in probability theory and statistics, particularly when dealing with multivariate data. Today's lecture covers several exciting topics. We will start with two random variables, exploring how they interact. Then we will discuss independent random variables where the occurrence of one does not affect the other. We will also cover conditional distribution, which describes probability given specific condition. Next, we will examine expected values, covariance, and correlation in order to quantify relationship between variables. So once again, a joint probability distribution describes the probability of two or more random variables occurring simultaneously, capturing the likelihood of different combination of outcomes. We have joint probability mass function for discrete random variables, and also we have joint probability density function for continuous random variables. In the case of discrete random variables, the joint probability distribution assigns probability to each possible pair of x and y through a joint probability mass function that we write it as probability of x and y. But in the continuous case, the joint probability is represented by a joint probability density function of f, x, and y, where the probability of the variables falling within a specific region or area or interval like A is obtained by double integration over that region. Joint distributions are fundamental in multivariate analysis, enabling the assessment of dependencies and interaction between variables. And these joint distributions are widely applied in fields like machine learning, algorithms, and also statistics, data science, and etc. So when dealing with two discrete random variables, we use joint probability mass function or joint PMF. This joint PMF is used to describe the combined probability of the two discrete random variables that we have. So if we have two random variables that they are defined on the same probability space, then the joint probability distribution is the corresponding probability distribution on all possible pairs of outcomes. For example, for the random variables like x and y, the joint PMF that we show in this way, so px and y is joint PMF, gives the probability that x values is equal to x and y values is equal to y at the same time, simultaneously. So in here, the probability mass function of a single discrete random variable like x specifies how much probability mass function is placed on each possible x value. So the joint PMF of two discrete random variables like x and y describes how much probability mass function is placed on each possible pair of values for x and y. So once again, if we have x and y as two discrete random variables and we define them on the sample space like A of an experiment, then the joint PMF, joint probability mass function that we show by Px and y is defined for each pair of numbers of x and y as Px and y is equal to Px is equal to x, y is equal to y. It must be the case that Px and y is non-negative. It is 0 or greater than 0. And always sum over x, sum over y, pxy is equal to 1. So these represent the joint probability of two random variables x and y that taking a specific value of x and y at the same time. The joint PMF is totally different by conditional probability. In the case of conditional probability, we say that what is the probability of y given x, right? So it means x has a given value that x, capital X is equal to x, then what is the probability that capital Y get this small y? But in the case of joint probability distribution, two random variables like x and y, they are taking some values like a small x and y at the same time, taking a specific value of a small x and a small y simultaneously. So this is different by conditional probability that we had already. Now let be any particular set consisting of pairs of x and y. So we have a pairs of x and y. For example, here we can say A is equal to x and y, where x plus y is equal to 5, right? Or we can say x and y, where max of x and y is equal to or less than 3. So this is pairs of x and y. Then the probability of x and y in A is that the random pair of x and y lies in the set of A is obtained by summing the joint PMF or pairs of A, right? So we can write in this way, sum of x and y in A, p, x, and y. This function applies to any set of x and y pairs in their sample space. Think of it as a table where each cell represents the probability of a specific outcome. This framework helps us understand how two variables behave together. Let's see an example next. Consider two dice rolls. In this case, the joint PMF, this is equal to probability of x getting I and y getting j at the same time, right? At the same time, simultaneously. So what is that? In here, both I and j are in this set, 1, 2, 3, 4, 5, and 6. So the probability of getting x, any of these values, and y, these values is equal to 1 by 36. Why? Because this one is 1 by 6, 1 by 6, so it is 1 by 36. Then in here, the marginal PDF of x, the marginal PMF of x, it means probability of x is equal to I is equal to sum of j from 1 possible value of j to 6, and each one is 1 by 36. 1 by 36, which is equal to 1 by 6, right? This is the marginal PDF. I will provide more about marginal PMF in next slides. So here is an example in the context of joint probability distribution for discrete random variables. We have two discrete random variables like x and y. This is an example of the bivariate probability distribution of the random variable for x and y. The first row that you can see here, this is the possible values for y. Y can be 0, y can be 1, y can be 2, and y can be 3. And the first column here, x, possible values for x. X can get 0, x can get 1, x can get 2, right? So the rest of the table that you can see here, these are joint probabilities. So this one, all you can see here, these are joint probability. It means probability of occurring x is equal to 0, y is equal to 0 at the same time is equal to k. The total probabilities here, so this is sum of each row is here, sum of each column is here, and sum of all is ATK, right? So the sum of all probabilities must be 1. So we can say ADK is equal to 1. So K is equal to 1 by AD. So in here, the probability of X is equal to 0 and Y is equal to 0 at the same time is 1 by AD. The total probability for x is equal to 0 is this one, right? So x is equal to 0 and y can get any possible value. This is the marginal probability of x is equal to 0. This is the sum of all these joint probabilities, which is 20k, right? It means 20 multiplied 1 by 80 is equal to 1 by 4, right? So the marginal of x equal to 0 is 1 by 4. Let's learn more about marginal probability in the next slide. To understand each variable individually, we compute the marginal probability mass function. For the variable like x, the marginal PMF that we write in this way, p underscore xx, is obtained by summing the joint PMF over all possible values of y, right? So in this way, this is all possible values of y, and this is joint PMF. And in the same way, we can do for y, all possible values of x and these joint. This process is like collapsing the joint PMF table along one axis to focus on one variable. So once again, the marginal probability mass function of a subset is the probability distribution of the variable contained in the subset. It means we consider each random variable individually. separately. This marginal probability mass function gives the probabilities of various values of the variable in the subset without reference to the values of the other variable. The marginal probability mass function is obtained from the joint probability mass function that we have for both variable x and y. Marginal is in contrast with the conditional probability. Marginal PMFs are essential for analyzing individual behaviors within a joint distribution. Let's see this in action. So in a couple of slides ago, we have found the joint probability mass function. So we have the total probability of 1, and we found here that k is equal to 1 by 80. Now let's find the marginal probabilities. Consider the first row here. We can see the sum of all is 20. It means if x is equal to 0 and y can get any possible value, then it is 20k. This result will be 1 by 4, right? So px is equal to 0. So we can write px is equal to 0, y is equal to 0 is 1 by 80. Px is equal to 0 and y is equal to 1 is 6 by 80, right? And in the same way, you can write the rest. For example, px is equal to 0, y is equal to 2 is equal to 9 by 80. And probability of x is equal to 0 and y is equal to 3 is 4 by 80, right? We can write here marginal probability of x is equal to 0 is equal to 1 by 4 sum of all these 4. So this refers to marginal probability of x equal to 0. And in the same way, for the first column here, we can do the same, right? So in here, we can write that probability of x is equal to 0 and y is equal to 0 is 1 by 80. Probability of x equal to 1 and y equal to 0 is 8 by 80. And probability of x equal to 2 and y equal to 0 is 1 by 80, right? Then we can write here the marginal probability for probability of y equal to 0 is this one, right? 1 by 8. This result 1 by 8 referring to the marginal probability of y is equal to 0. All right, now we want to practice in Python. So import numpy as np, matplotlib, pyplot, cboard, sns, and pandas pd. So next, we set random seed for reproducibility. np.random.seed, and here 42. Then here it should be seed. Then I'm gonna define x values and y values. X values equals to, what do we have? 0, 1, and 2, and y values are 0, 1, 2, and 3. Next, we're gonna solve for k. We wanna find the value of k. Joint underscore PMF of k is equal to np.array, and in here, so these are the coefficients 1694, 8, 18, 12, 2, and 1694 based on the table that we had in our slide. Now I'm gonna find the total sum k. Total sum k is equal to np.sum of joint PMF over k. Because our total probability is 1, so value of k is 1 by total sum k, right? And then joint PMF is equal to joint PMF k multiply k, that 180. So these are the values for joint PMF. So we can print if the value of k is equal to k, which is 0.0125, right? We can have a heat map law for joint PMF of x and y. SNS dot heat map, and then here we will pass joint PMF anode is equal to true, and the rest. So here we go. These are the values for, based on our table that we have, these are the joint PMF where k is equal to 1 by 80. Next, I'm going to compute marginal PMF. So marginal of x is equal to np.sum, and in here joint PMF and x is equal to 0 because the x values are in axis 1 and y values are in axis 0. So sum over y for each x and sum over x for each y, right? So let's print marginal of PMF for x is these values, and we can do the same thing for y. So y, and in here y, then here y values, and marginal of y. So these are marginal PDF for y. Let's also plot them. So here, plt dot subplot of 1 to 1, and in here I'm gonna plot x values marginal x and y values marginal y, and here I go for green, for example, different color. So here you can see this is the marginal values of x and marginal values of y. In many situations, information about the observed value of one of two variables x and y gives information about the value of the other variable. Here we can see the same definition for independence of two random variables. So random variables like x and y are independent if their joint distribution factors into the product of their marginals. In here, we write down that probability of x is equal to x, and y can get the value of y is equal to probability of x, probability of y. In here, independence means the behavior of one variable does not influence the other, simplifying probability calculations. So once again, two random variables like x and y are independent if for every pair of x and y values, probability of x is equal to x, y is equal to y is marginal of x and marginal of y, right? It means two random variables are independent if their joint PMF is the product of two marginal PMF. So this is joint, this is marginal, and this is marginal. So random variables x and y are independent if their joint PMF is equal to marginal PMF of x multiplied marginal PMF of y. Intuitively, independence says that knowing the value of one of the variables does not provide additional information about what the value of the other variable might be. Now, based on the table that we had already, we want to find whether our x and y are independent or not. To do that, we need to find the probability of x equal to x and y equal to y. This equals to the product of marginal probability of x and y. So based on the table, we found that our k is equal to 1 by 80. Now, then we find the marginal probability of x. Just I write them down, px0 is equal to 1 by 4, probability of x1 equals to 1 by 2, and probability of x2 is equal to 1 by 4, right? And we found the marginal probability for y, py equals to 0 is 1 by 8, py1 equals to 3 by 8, py2 equals to 3 by 8, and py3 equals to 1 by 8, right? Now we need to find the joint probabilities. It means combination of all. It means p0 and 0, p0 and 1, p0 and 2, p0 and 3, then p1 and 0, p2, p1 and 1, p1 and 2, p1 and 3, right? So just, we find based on the table that we have, so p0 and 0 is k divided by 80k, divided by total, right? So it is 1 by 80. The next one is 6k divided by 80k, which is equal to 3 by 40. So I will write down the rest, just 9 by 80, then 1, 0 and 3 is 1 by 20, then 1 and 0 is 1 by 10, then 1 and 1 is 9 by 40, then 1 and 2 is 3 by 20, and 1 and 3 is 1 by 40. We move to 3, so p2 and 0 equals to 1 by 80, p2 and 1 equals to 3 by 40, p2 and 2 equals to 9 by 80, and p2 and 3 equals to 1 by 20. We're gonna check independence based on this equation, right? So we will find them out. Probability of x0 and multiply probability of y0 is equal to px0 is 1 by 4 here, multiply py0, this one, 1 by 8, equals to 1 by 32, right? We can write this one in the same way like 2.5 out of 80. This is equal to this one. And our P0 and 0 is 1 by AD, so they are not equal. Okay, so the one condition has been violated. Or in case of, for example, px0 and py1, so px0 is 1 by 4, 1 by 4, and py1 is 3 by 8. So these two are equal to 3 by 32, which is equal to 7.5 by AD. But our P0 and 1, this one is 3 by 40. So they are not equal. And also, for example, we can check for Px is equal to 1. So Px1 and Py1 equals to 1 by 2 and 3 by 8, right? 1 by 2, 3 by 8 equals to 3 by 16, that we can write it as 15 by 80. But the probability of 1 and 1 is equal to 9 by 40, right? Or you can say 18 by 80, but they are not equal. So these two x and y are not independent because the joint probabilities do not match the product of marginal probabilities for this pair. Then x and y are not independent. Okay. And here I want to check whether these x and y are independent or not. So is independent is equal to true by initially, later we change it. So independence difference is equal to np dot zeros like and joint PMF. Right? Then for I and x in enumerate of x values, for j and y in enumerate of y values, then the expected is equal to marginal x I multiply marginal y j, right? Then we add to independence difference. Independence difference I and j is equal to joint PMF of I and j minus expected. If not, NP is closed, just check if they are closed or not. And this is a very small value to check the tolerance. Then it is false, right? Marginal. Okay, so now let's pass our x and y. So let's check print if our x and y independent. It's false. They are not independent. So the next topic here is CDF, or cumulative distribution function, for joint probability distribution of discrete random variables like x and y that we have. So we write in this way: f x and y of x and y is equal to probability of x less than or equal to a small x and y less than or equal to a small y. For discrete random variables, this is computed by summing the joint probability mass function over all possible of x and y. So this one is f x and y of x and y is equal to sum of xi less than or equal to x and yi less than or equal to y. Probability of x is equal to xi and y is equal to yj, right? So this one should be j. This here, x is equal to xi and y is equal to yi, is the joint PMF, and the sums are taken over all possible values of xi and yi. Based on the properties fx and y, f x and y is something between 1 and 0. So in the case of marginal CDF, we write in this way is equal to f x and y for x up to plus infinity is equal to sum of xi less than or equal to x. Probability of x is equal to xi. And in the same way, the marginal CDF for y is fy of y is equal to f x and y from infinity to y is equal to yj is less than or equal to y. Probability of y is equal to yj. So this is how we can find the CDF for joint probability distribution. Next, I'm gonna compute the CDF. So CDF of x is equal to NP, and in NP we have a function called as COM_SUM, cumulative sum for marginal values of x, and the same thing, CDF of y is equal to NP dot COM_SUM marginal of y. All right. So then let's print them. Print marginal of x and print marginal of y. So in here y. So these are the marginal CDF for x and marginal values for y. Now we can go for a step function for CDF, right? PLT subplot 1 to 1 to 1, and in here PLT step, right? X values CDF post after each value, if we will have a increase, color red and color blue. So here you can see a step for CDF X and CDF Y. Now I'm gonna find joint CDF. So joint underscore CDF is equal to NP dot zeros. Zeros like this is a function based on the joint PMF that we already found. So therefore I in range of length of x values, and for j in range of length of y values, then I'm going to calculate joint CDF I and j as NP sum of PMF up to I plus 1 up to j plus 1. Okay. Next, I'm going to print these values in a Panda data frame, pt.data frame, and in here I will get joint CDF, index x values, column y values, and I will convert them to string. So you can see here, these are the values. I can plot the heat map. So heat map of joint underscore CDF, anode is equal to true, FMT, and the rest is the same. So here you can see this is the heat map for CDF. I also can plot it like a surface, right? So let's say fig is equal to plt.figure, fig size is equal to 5 and 5. Then x, it's okay. This one is okay. Then NP mesh grid. Now here ax dot plot surface, and you can see here this is a surface plot for CDF. So you can see here this is the value of y from 0 to 3, value of x from 0 to 2, and here is the value for CDF. So you can see here at this point it is 1. When dealing with more than 2 random variables, we define a joint probability mass function. For random variables like x1, x2, x3 up to xn, the joint PMF that we show in this way is their combined behavior. This generalized our two variable framework, allowing us to model complex systems. So once again, we have random variables like x1, x2, x3 up to xn, and they are independent. It means their joint PMF equals to the product of their marginals. For example, probability of x1, x2, and x3, this equal to probability of x1 multiply probability of x2 multiply probability of x3. These must hold for all subsets, pairs, triples, and so on. So let's discuss independence in this context. Random variables x1, x2 up to xn are independent if the joint PMF of any subset is equal to the product of their marginals. So the notion of independence of more than 2 random variables is similar to the notion of independence of more than 2 events. If the variables are independent with, for example, n is equal to 4, then the joint PMF of any two variables is the product of the two marginals, and similarly for any three variables and all four variables together. Intuitively, independence means that learning the values of some variable does not change the distribution of the remaining variables. Most importantly, once we are told that n variables are independent, then the joint PMF is the product of the n marginals. Independence simplifies analysis significantly as we can treat variables separately. Next, we will look at conditional distributions. Conditional distribution describes the probability of one random variable given the value of another one. So for discrete random variables, we use conditional PMF to model how the distribution of one variable changes when another is fixed at a specific time. It means we have the value of the second one. This is useful in applications like predictive modeling and decision making. In other words, a conditional distribution captures how the probability of one random variable is influenced by the value of another one. So suppose we have two random variables x and y, and suppose x is the number of months a bicycle front tire lasts, and y is the number of the months that the rear tire lasts. Suppose we know that x is equal to 10, it means the front tire lasts for 10 months, then what is the probability that y is less than or equal to 15? It means the rear tire lasts at most 15 months. Additionally, what is the expected lifetime of the rear tire if x is equal to 10? These questions can be answered using conditional probability. So our x and y are two discrete random variables, and they have a joint PMF, and the joint PMF is probability of x is equal to x and y is equal to y. And we have a marginal PMF for x, which is equal to probability of x, and this probability of x is equal to sum over possible values of y and joint PMF. Probability of x is equal to x and y is equal to y, right? And marginal PMF for y, which is equal to y is equal to sum over all possible values of x and their joint PMF, right? So in this case, with these conditions, then the conditional probability is probability of y is equal to y given x equal to x is the joint probability divided by marginal probability of x. And in the same way, the probability of x is equal to x given y is equal to y is equal to their joint PMF, x is equal to x and y is equal to y divided by marginal of y. And we know that this y is equal to sum over x of x is equal to x and y is equal to y, and this value should be greater than 0. Okay, here is an example. Suppose x is the outcome of one die when we roll two dice together, and y is the outcome of the other one. So in this case, joint PMF is uniform here. So P x is equal to I and y is equal to j. This is 1 by 6, so 1 by 36. And we know that I and j are in 1, 2, 3, 4, 5, and 6, right? Then the marginal PMF of x equals to probability of x equal to I is sum our possible values for y. J is equal to 1 to 6, probability of x equal to I, and probability of y is equal to j, which is equal to 6 by 36 is equal to 1 by 6. And marginal PMF of y is equal to probability of y is equal to j, it's equal to sum of I from 1 to 6, probability of x equal to I and y equal to j, which is equal to 6 by 36 is equal to 1 by 6. And suppose I want to find what is the probability of x equal to 3 given y is equal to 4. So probability of x equal to 3 given y equal to 4 is equal to join PMF, probability of x equal to 3 and y is equal to 4. It's somehow intersection, right? By marginal probability of y is equal to 4, right? So this one is 1 by 36 and this one is 1 by 6, which is equal to 1 by 6. Based on this table, we want to find probability of x equal to x given y is equal to y, right? In this case, we just divide the joint probability by the marginal probability. So for example, what is the probability of x is equal to x if y is equal to 2? So all possible values of x, y is equal to divided by y is equal to 2. So what are the possible values for x? X is equal to 0, x is equal to 2, x is equal to 3. If x is equal to 0, then probability of x is equal to 0 and y is equal to 2 is 9k, 9 by 80. We already found that k is equal to 1 by 80, right? And probability of y is equal to 2 is this one, right? Sum. So it will be 0.3. The next case is probability x equal to 1. In this case, probability of x equal to 1 and y is equal to 1 is this one, 12 by 80. And it divided by probability of y is equal to 2, 30k, which is 30 by 80 is equal to 0.4. And in the last case, x is equal to 2, y is equal to 2 is 9 by 80 here. Marginal probability of y is equal to 2 is 30k, so it is equal to 0.3. In this way, we can find the conditional probability. Now, I'm going to calculate the conditional PMF. So x e dx is equal to 1. Then conditional y given x1 is equal to x equal to 1 is joint PMF of x multiply marginal of x IDX. Or, for example, if I want to find the conditional probability of x given y is equal to 2, IDX is equal to 2, then conditional of x given y is equal to 2 is joint PMF of x and y index by marginal of. So it means in here, we go for all possible values of x that y is equal to 2. So now we can print them, print conditional PMF of p equals to y equals to y given x is equal to 1 is this one. And for the next, we can go for this. Okay, so these are the value for conditional PMF. Next, we're gonna discuss expected values. So the expected values of a function like hxy of two random variable is weighted average. So this is called as weighted average. And it's equal to sum over x, sum over y, hx and y multiply probability of x and y. Once again, if we have x and y as jointly distributed random variables and they have a PMF of probability of x and y, so then the expected value will be calculated in this way. Expected values help us summarize joint behavior like computing means or moments. So now I'm going to calculate the E of x and E of y based on our example that we have. So we found that k is 1 by 80 and E of x here is the expected value of x, which is equal to sum over x multiply px is equal to x, right? So this is the marginal probability of x. So we're going to calculate marginal probabilities. X is equal to 0 is equal to, based on our table, 20k, which is equal to 20 multiply 1 by 80, which is 1 by 4. And the same way, probability of x is equal to 1 is 40k, and here 40 multiply 1 by 80 is equal to 1 by 2. And probability of x equal to 2 is 20k, which is 20 multiply 1 by 80 equals to 1 by 4. Now we can compute the E of x. So E of x equals to 0 multiply probability of x equal to 0 plus 1 multiply probability of x equal to 1 plus 2 multiply probability of x equals to 2. And then e of x is equal to 0 multiply 1 by 4 plus 1 multiply 1 by 2 plus 1 multiply 1 by 4, and it is equal to 1. Sorry, here it should be 2. So 2, it will be 1 by 2 plus 1 by 2 is equal to 1, right? So e of x is equal to 1. Now we're going to calculate the e of y. So e of y is the expected value of y. So we can write e of y is equal to sum of y dot py is equal to y. So the marginal probability of py is equal to py is equal to 0 is equal to 10k based on our table. Is 10 multiply 1 by 80 is equal to 1 by 8. Then probability of y is equal to 1 is equal to 30k, which is equal to 30 multiply 1 by 80, that is 3 by 8. Probability of y equals to 2 is equal to 30k again is equal to 30 multiply 1 by 80 is equal to 3 by 8. And probability of y equal to 3 is equal to 10k, which is equal to 10 multiply 1 by 80 is equal to 1 by 8. Then e of y is equal to 0 multiply p of y is equal to 0 plus 1 multiply p of y equal to 1 plus 2 multiply p of y equal to 2 plus 3 multiply p of y equal to 3. So we sum up them together, then e of y is equal to, this one will be 0 plus 3 by 8 plus 6 by 8 plus 3 by 8, it is equal to 3 by 2. So e of y is equal to 1.5. In a separate slide, I'm gonna find the standard deviation of x and y. So we found already that k is equal to 1 by 80. So, and we find that e of x is equal to 1 and e of y is equal to 3 by 2, right? So in order to find variance, we need to find ex square, right? And ex square is sum over x square dot pxx, right? Just we say x is equal to 0, then 0 square multiply 1 by 4 is equal to 0. If x is equal to 1, 1 square multiply 1 by 2 is 1 by 2. And if x is equal to 2, then 2 square multiply 1 by 4 is equal to 1, right? So ex square equals to 0 plus 1 by 2 plus 1 is equal to 3 by 2, right? And we can calculate variance of x. Variance of x equals to ex2 minus e of x square, all square. So here we found that here is 3 by 2 minus 1 square, it's equal to 1 by 2. So there is sigma of x equals to variance, root square of variance of x, which is equal to root square of 1 by 2 is root square of 2 by 2. We can do the same thing for y here. So e of y square is equal to sum over y square dot py. So we do the same, y can be 0, y can be 1, y can be 2, y can be 3, right? So 0 square, 0 multiply marginal of y0, 1 by 8 is equal to 0. 1 square multiply 3 by 8 is equal to 3 by 8. 2 square multiply 3 by 8 equals to 3 by 2. And 3 square multiply 1 by 8 is equal to 9 by 8. Then we will sum up them together. So e of y square equals to sum of all together 3, 12, 19, it will be 24 by 8 equals to 3. Then variance of y equals to e y square minus e of y all square. So it will be 3 multiply 3 by 2 is square, which is equal to 3 by 4. And standard deviation of y is equal to variance of root square of 4, which is equal to root square of 3 by 2. So this is sigma y and this is sigma x, right? In order to find h, x, and y, we need to have one function like h, x, and y, right? So this expression that you can see here, this is the expected value of a function h, x, and y of two random variable x and y that we calculate by summing the function's value that you can see here at each pair of x and y. So this is sum over y, this is sum over x, and then weighted by the joint probability here. We can use this one in probability and statistics to analyze outcomes in scenarios like risk assessment, decision making, or modeling dependencies, such as predicting financial returns or evaluating joint behavior in machine learning. We can also compute the expected value. So E of x is equal to sum of x multiply p for x and p in zip of x values and marginal x, and the same thing for y. So let's print them. Expected value of x and expected value of y. This is 1 and 1.5 that we find. This sets the stage for covariance and correlation that we're gonna study in the next slides. So here is covariance. Covariance measures the linear relationship between two random variables. So for example, if we have random variables like x and y, then covariance of x and y is equal to, we can write it in this way. So covariance of x and y is E of x minus E of x, right? Multiply y minus E of y, and this can be simplified as E of xy minus ex multiply ey, right? So in this case here that we have written here, E of x and E of y, they are expected values for x and y. Ex and y is the expected value of product of x and y. A positive covariance indicates that x and y tend to increase together. It means while one is increasing, the other one is increasing. If we have a negative covariance, suggests an inverse relationship. It means one increase, the other one decrease. So when two random variables are not independent, so the condition here is they should be dependent, right? So they are not independent, and it is frequently of interest to assess how strongly they are related to each other. It means if one is increased, what is the behavior of the second one? We can also rewrite covariance of x and y of sum over x, sum over y, x minus mean of x, y minus mean of y, multiply probability of x and y. This x minus mu x, y minus mu y, they are deviations of the two variables from their respective mean values. So the covariance is the expected product of the deviations. Covariance of x and x is equal to E of x minus mu 2, which is equal to variance of x. So once again, suppose we have x and y, they have a strong positive relationship to one another, by which we mean that large value of x tend to occur with large values of y. And on the other side, small values of x with small values of y. Then most of the probability mass function will be associated with x minus mu x and y minus mu y. Either both positive, it means both x and y above their respective mean, or both negative. It means both x and y below their respective mean. So the product of x minus mu x and y minus mu y will tend to be positive. Thus, for a strong positive relationship, covariance of x and y should be quite positive. For a strong negative relationship, the sign of x minus mu x and y minus mu y will tend to be opposite, yielding a negative product. We can simplify the covariance in this way. Covariance of x and y is equal to expected value of x multiply y minus mu x multiply mu y. Covariance is a building block for correlation, which we will explore next. The correlation coefficient, or rho x and y, or simply rho, this normalized covariance to lie between -1 and 1, and we find correlation x and y, or rho x and y, is equal to covariance of x and y divided by sigma x, sigma y. And you know that sigma x, sigma y is the root square of variance. If rho is greater than 0, then we say this is positive, right? So it means x and y moves in the same direction. If rho is negative, it means the x and y are not in the same direction. And if rho equals to 0, it means x and y are uncorrelated. It means there is no linear relationship between these two variables, even though they may be still dependent. So dependency and correlation are totally different. We use this correlation coefficient to measure how strong a relationship is between two variables. So if x and y are independent, then covariance of x and y is equal to 0, but the converse is not always true. Once again, correlation is different by independence. Two variables may be independent, but they have correlated, or the other case. Can see the pictorial representation of possible values for covariance: positive covariance, negative covariance, and zero covariance. Covariance depends on both the set of possible pairs and the probabilities. When we say positive covariance, it means this is a perfect positive relationship. It means as x increases, y also increases. You can see here in this way. It means both variables x and y tend to be high or low at the same time. If x increases, y also increases. If x decreases, y also decreases. Here you can see a negative covariance. It means perfect negative linear relationship. The movement of one variable is the opposite side of the other one. So as x increases, y decreases. So this is called as negative. And here we have zero covariance, no linear relationship. In this case, two random variables like x and y are independent. It means they do not follow the trend of each other. So we already learned that variance shows the difference between each data value and their mean. For example, here mean is 2.58, and the variance is the distance between different values to their mean. And for this here, this is 2.4. So we find the variance as the difference between different values up to their mean. However, covariance shows how the variable change according to each other. So in here, as x increases, y also increases. So in this case, rho is positive. And the correlation is the upward trend that indicates a likely positive correlation. And it measures the strength and direction of the relationship. So the correlation is driven by standardizing covariance with the variable's standard deviation, and it ranges from -1 to 1. The expected value of x is equal to 1, and expected value of y is equal to 1.5. So we have if y is equal to 0 and x is equal to 0, so x multiply y is equal to 0, and the probability is 1 by 80, right? Based on the table that we had. So x is equal to 1, x multiply y is 0, and 6 by 80 is the joint probability. Again, 0 joint probability, 0 joint probability, 0 joint probability of x equal to 1, x multiply y is 1, and this is the joint probability, and so on, right? So this is the second table. We just summarize all possible x, y, and their corresponding probabilities. So for example, for x is equal to 0, so we have one case here, 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 one case here. If you sum up them together, you will come up with this one. So for 1, we have only one case here, that is 18 by 80. For 2, we have two cases, that we have 18 by 80. For 3, we have one case, 2 by 80. For 4, we have one case, 9 by 80, and 6, one case, 4 by 80. Then the expected value of x multiply y is x multiply y multiply probability of x dot y. So for this is the weighted average. So for the 0, we find this one. So 0 multiplied 29 by 80. For 1, 1 multiply 18 by 80. For 2, 2 multiply 18 by 80. 3 multiply 2 by 80. 4 multiply 9 by 80, and sigma. And if you do this calculation, you will come up with 1.5. Then covariance is equal to expected value of x multiplied y minus expected value of x, expected value of y. So we find that expected value of x, y is equal to 1.5 minus expected value of x is equal to 1 and expected value of y is equal to 1.1 and the covariance is equal to 0. Then the correlation is covariance divided by sigma x, sigma y. So it is 0 and covariance is 0. It means there is no relationship between variable x and y. Next, I'm gonna find covariance. So covariance of x and y, initially it's equal to 0. Then we're gonna find covariance contributions, and initially we make it as zeros like as in the side in as joint PMF, right? Then for I and x in enumerate of x values, and for j and y in enumerate y values, then contribution is equal to e minus ex plus e minus ey multiplied joint PMF based on the equation that we already tried. Then in here we can say covariance contributions of I and j is equal to contributions, right? All right, now we're gonna print it. So print f covariance of cov x and y is cov x and y with 4 decimal points. Okay, it's 0. And we can also go for heat map. So SNS dot heat map of covariance. And you can see here, this is covariance table. Okay, let's recap today's key concept. We covered joint and marginal PMF for discrete random variables. We studied independent random variables and also conditional distribution. We also explored expected values, covariance, and correlation in order to quantify relationships between different random variables. These tools are foundational for statistical analysis. Thank you very much for your attention. If you have any question or if you want to discuss further, please reach out by leaving a comment below this video lecture. I'm here to help you master probability and statistics. Have a great day, have a great night, and see you in the next lecture.